Our next speaker is Alberto Miranda Bedate. Speaking on the topic of silent stewardship, making fair compliance invisible with agentic workflows. He's at the Amsterdam University Medical Center and is going to be sharing about AI and the potential it offers to automate the research lifecycle in this practical application and enforcing fair principle and which remains underdeveloped.
Thank you very much, guys. My name is Alberto. I'm here. I'm a data steward and fair data automation developer. What this function means, I hope that by the end of this presentation, you have a kind of idea what it is about. And yeah, before starting, I would like to thank the organizers of the conference, because it's a real pleasure to be here and to be presenting here. And also thank you to Miranda, who make all the administration to put me here. Thank you. Well, yeah, I'm going to talk to you about the silent stewardship, making fair compliance invisible with agentic workflows. And I hope that it serves as a kind of practical example of what we were talking about during these 2 days, about how AI can help us standardizing the metadata in the different domains. Just one disclaimer. So this is academia, so a more chaotic world. I would say that what industry is, and it is more. Because of that, it's more researcher centered. So what you will see would be less JSON files, less this type of data scientist formats, and more free text things. But we can translate it afterwards to this type of machine readable formats. First of all, I am embedded in this group, the ACDC. Yes, I'd say it's ACDC. It is, and yes, it is because of the rock music group, but it's not just because of that. It stands for Advanced Compute and Data Core. It is the advanced compute part is led by Dr. Dalsey, and the data core where I am embedded with my colleagues led by Katie Wollstonecroft. And together we are working to all the core facilities, not limited to, but with all the core facilities at the Amsterdam UMC. You can see that there are 5 different, well, these 4 and 2 repeated because we have 2 different locations. You can see the proteomics, genomics, metabolomics, and also 2 MCCF, microscopy and cytometry core facilities. You can see this box in the middle of them. It is where ACDC resides, and it's trying to make the data produced in these core facilities in a more fair manner. And we are doing by supporting the data lifecycle under the FAIR principles. You probably know this scheme from Elixir resources. We try to make the researcher to think about the experiments in advance, not just during the process of making the experiment. So we want the researcher to think on the planning at the very beginning, how to collect the data, of course, how to process and analyze it, and at the end, how to preserve, share, and reuse it. And we do it based on existing standards and tools. We are not trying to reinvent the wheel, though we are trying to implement also the new technologies if they are enough useful for us, for our objectives. And for example, we are using these resources like the fairsharing.org for community and metadata standards. We are using the Elixir data management toolkit for some recommended tools. And of course, our colleagues in the AC side are providing HPC resources to the researchers in order to make all the analysis and all this homogenization possible. Just a little bit of numbers of what we are dealing with at the MCCF. My personal case, I'm working a lot with this core facility, mostly focused on flow cytometry. And well, here I'm going to focus in this technology, but we are making it extendable to the rest of the multi-omics technologies. You can see there is a central hub with 3 satellite labs, have a strong collaboration with the Vrije Universiteit, which is in the neighborhood. Some numbers, we have 12 operators, 13 with me as data steward in there, 36 plus instruments. I think there are 2 new coming during the last week. And again, more than 500 active users and more than 70,000 hours of support per year. So it's a huge task. It's not something that we can do in just one day or with just one person. The focus of the MCCF is wide as well, immunology, oncology, and neurology. And we are collaborating with the usual suspects in the field of imaging and cytometry. Already in the MCCF, they have these support steps: experimental setup, choosing the right technique, the data acquisition with trainings one-on-one with the operators, and also in the data analysis, they have dedicated bioinformaticians available for the researchers. And this can cover already perhaps these first steps of the data lifecycle, and where we are trying to give some input is in this last part of the data lifecycle, so in the preserving, sharing, and reusing, by automating backups, particularly from pipelines, on data management, and the verification of the experiments. Main challenges that we have there, well, you see them here. The growing size, an amount of data sets that are being produced, it's a core facility, so you can imagine that is constant flow of new experiments coming in. And the challenges in user support, it's difficult to handle the quality control of the data produced by these users. The instrument diversity in formats is increasing exponentially with use. So every year you get two or three new formats with 2 or 3 new machines. So it's something that you have to incorporate in your normal flow of work. And these two last are kind of really important ones: the low adoption of international standards and the loss of opportunities, because we want also to give this multi-omics approach to the core facility. So not just making this silo, but connecting the silos together in order to see new integration capabilities. For this presentation, I have decided to talk more about this problem, and more concretely about the MiFlowCyt standard. We'll tell you more in the next slides. And for that, I present you Flow Repository. This is one of the mainstream catalogs for flow cytometry experiments, where you can query and download data. It's uploaded by the user, and it is annotated by this MiFlowCyt standard. MiFlowCyt stands for minimal information about the flow cytometry experiment. This repository has been developed by the ISAC, the International Society for Advancement of Cytometry, more than 10 years ago. You can see that it's a clean landing page with a query box where you can put one word, then you get a list of experiments, and when you navigate through those experiments, you get the description of the experiments with the MiFlowCyt standard fields. Also, you can see here in the upper left side of the screen, the yellow download button, by which you can download the FCS files, which is the typical raw format of flow cytometry. However, we have identified several problems. The first of which is this repository has been developed in Ruby Rails languages, which is no longer mainstream language. Was 10 years ago, 15 years ago, but now you need really specialized people on this. So the developments on this catalog has been frozen for several years already. The second is the difficulty of use. This is one of the most frequent claims from the users. It is a lengthy process to submit an experiment. And according to the paper and according to the users as well, you have to spend at least half of an hour on a really simple setup, couple of samples, a couple of conditions. And it can go up to several hours also if the setup complicates a little. So it's something that should be improved. It's not that we made, it should be improved. And it relies on the slow adoption of the standard, because if the repository is not being used, this standard is no longer useful. And the last but not the least, 2 simple queries. I just show you. Just put one keyword to get a list of experiments, and here we go. The world is yours. You don't have nothing else to filter out these experiments further, but navigating through all the experiments and looking for what you are trying to find. So for that, together with the ISAC members and the data management task force of the ISAC, we wanted to provide this solution for repository 2.0. We have changed the framework into Python does completely. We are going to make the local database for the experiments of the Amsterdam UAC, plus an exact copy of the global database for searching purposes. And around this Flow Repository 2.0, we have developed, and that's what I'm going to show you in the next slides, a fully automated pipeline that goes from the machine, from the cytometer, to flow repository itself. But before going into this pipeline, this is it. This is MiFlowCyt. This is how it looks like. It's a text document. You can see that there are 5 perfectly differentiated headers: experiment overview, sample description, instrumentation behind that, reagents and data analysis. We can transform this into a JSON format. That's what I meant about the researcher-centered approach for this. And as you can imagine, we rely a lot on the input of the researcher for most of the fields in here. But there is a small part that could be luckily acquired from the FCS files, because FCS files is already a standard in itself. This flow cytometry standard, these editors. And we can obtain all this technical information from the files themselves of the experiment. So here they are, 2 different inputs. The researcher one, it could be a research plan, experimental description. It is free text already, because that is the normal way of that the researcher saves their experimental descriptions. And on the right side, the site. I'm going to start from this side here, because in the scope of ACDC, I have developed this quality control tool that makes quality control analysis for each of the files produced in the core facility. And after this quality control has been made, together with our other development, this backup tool, it migrates both data control quality, data control analysis, and the FCS files towards the central storage at the Amsterdam UNC. So we are making automatically moving the raw data from the cytometer to the storage. On the other side, we have the HPC from our colleagues in the group, Elias, where I have developed this agentic workflow that would ingest both inputs, would convert them into MiFlowCyt standard, and would put them in both flow repository and would feed another of our developments, which is the RAG tool for making queries in natural language. Eventually, in the next months, I will work to integrate this RAG tool into flow repository as part of the new developments of flow repository 2.0. What does this agentic workflow do? Well, we have here the experimental description and free text from the researcher will be ingested into the local environment, the local computer, HPC cluster in this case. And we have scripted some queries, which would be the fields of MiFlowCyt. Small language model will extract literal sentences from the report corresponding to those prompts, and it would generate a MiFlowCyt standard. We have put also in place human in the loop, because we want the researcher to check that the extraction of the fields are indeed what the researcher expects. For that, we are using these open source tools. So Llama as the tool that deploys the language models, and RAGflow as our RAG engine. Though this is going to be migrated with some of other developments that are taking place in the Amsterdam EMC, but this is what we have so far. And altogether, give these 3 main characteristics to the system. First of all, it's literal extraction. I insist on this. We are not using generative properties of the AI models. We are extracting literally the sentences or the description of the research about the experiment. It is local. So we are hosting these models in the HPC. So it is under the Amsterdam UNC privacy rules. So it is also suitable for clinical data without any problems. And the third, I think it's an interesting one because it can be run low in computers. So this computer can be run because we are using small language models that do not require that much computer capacity as the bigger ones. Some of the models that we've been testing in the left side, the Llama 3.2 model, the Alibaba models, UN, all these versions, European representative, the Mr. Ministral, Chinese representative as well, DeepSeek, Gemma 3 and Gemma 4 from Google DeepMind, and GPT OSS from OpenAI, with the releases, the most recent releases of these models. All of this has been tested in this system. And this is how it works. I'm going to give you not a live demo, but I will show you how it works. So this is Flow repository. If the video goes in. So you go to submit your experiment, and here appears the screen for submitting the experiment. I'm going to stop here. One moment, because you have here a second option, which is if you have a MiFlowCyt form already, you just browse into that, upload it. In less than 30 seconds, you have the experiment in the database. So it is a really big gain from the minimal 30 minutes that you need to incorporate an experiment up to several seconds to have it uploaded and submitted to the database. Let's move forward for the AI-assisted pipeline. So we need the, I think it's running, not. Here it is. This is the input, FCS files before responding to the experiment, the free text description in the same folder. This is how the description looks like. We have decided to have a paper-like format. See the abstract, there's methods, results, discussion, plus the title, authors, and several metadata fields that are needed for to complete the MiFlowCyt standard. It is as simple as browse folder where these files are contained. You select it, you run the department. Here you can skip out the man in the loop view, because in the middle, you can check what the model has extracted, and you run the pipe. Now it is running in approximately than a minute. The document is ingested. We are not going to wait that minute. I'm going to jump in time here. And this is what happens after the document has been ingested. Look, querying different metadata fields, the research title, the purpose, primary researcher, so on and so on and so on, asking about fields that are needed for the MiFlowCyt standard. I have made specific dedicated queries, for example, for reagents. It's a more complicated kind of field, and I don't want the model to suffer from attention diffusion, a lot of context that reduces the quality of the structure. So here's a dedicated query from the reagents. And at the end, another part of the agentic workflow, an orchestrator will pick up all the fields that has not been extracted or are not clear in the first query, and it's going to be requered, because we would increase the efficiency of the search, because it is a more dedicated. And here it is, on the loop, free text boxes from all the queried fields. You can modify as you wish, you can change it, you can eliminate it, and if you agree with all of this, confirm and upload. Sending fields 30 seconds later in the database. This is how we have automated the process of generating the standard and uploading it to the database. So, summary up to here, 70 minutes, we're good on time. So we have moved the Ruby Rails framework to the Python one. There are reasons for this. More people can potentially contribute nowadays. We can keep a good pace of development. And this is an important part, because this would be the second part of my presentation about. So we can couple other tools easily into this framework. We have also aimed to increase the MiFlowCyt standard adoption by easing the creation and submission of the new experiment by Agentic AI and automating and sorting. So this is what we have gained so far. And regarding this coupling other tools, here I can put the magic word, knowledge bases. That's exactly what we are doing. For repository 2.0, we want to incorporate this knowledge base that is coming from the very same database of the global repository. We like to use, or at least I like to use Neo, because it's really beautiful how you can expand the things, you can search for them. It also has a really nice query language, which is Cypher. You will see an example later on. I will show you this. I'll leave it the data model, how it looks like. These are the experiment nodes. Let's expand this. See all the different nodes related to it, all the triples related to the experiment. I'm going to order this for you. For example, keywords in the yellow nodes. Have here panels for the flow cytometry. Have samples. Have the instrument here. I have created an FCS vault, not to collapse the whole view of Neo4j. Also the organization, here some DOIs from the publication, a lot of different other projects that are related to this very first one that has in common that blue node, which is a problem. At the end, it's also important, authors that have contributed to all these experiments. This is more or less from a high level how the data model looks like in this case. But why? We have made this effort. We want to improve the query. That's one of the things that we wanted to also address in one of my first slides. We want to solve these kind of questions. Really straightforward questions that any experimentalist would like to know. Which is the most used reagent for detecting CD14 in human liver in Aurora 5L cytometry? You want to make a good your experiment. You want to use something that you know it works. So let's check in the database how it is done. But with the simple query that I have shown you before, can't do this. But you can do it, but it would cost you really a lot of time to go one-on-one through all the experiments. And in place, we would like to have a list of experiments that have been using, or at least to know which is that reagent concretely. So, however, this is a problem because we have a multiple query. Multiple means that you are jumping to different tables of the SQL database. So experiment is related to cytometer, experiment has internal as well sample. Sample is related to source, reagent, organism. You see in bold the things that are key to the question. And SQL database is not that way. Doesn't matter. Let's solve this. It's not that efficient with this type of queries because it collapses the RAM. Complexity of the query is less efficient in terms of speed. And here I have an example how the query looks like. Next time you have the SQL query for that question. Have different join tables. So imagine that we are joining more than 2,000 entries at least for each join together. So the RAM usage increases, the speed is lowering. And look how short and beautiful looks in Cypher, which basically mimics the data model of the database. So there is a gain on having this system in place for these complex queries. However, we have a problem because we are in premium, and while we have fixed the fields by the standard, the researchers have the metadata in a free text manner. And that creates some semantic alignment problems like this. We would like to solve that question, have exactly this type of not mistakes, but problems to homogenize the database. So H sapiens, human, and Homo sapiens should be a single concrete concept. And therefore, we're trying to normalize the database, so to correct the lithology terms with the OLS source, germ, because of other reasons. I think is where AFO and ISM could play a role as well, because we are still in the process of deciding which could be the best way of approaching this. And this is what we are doing. The SQL database will remain immutable. This is the source of truth. The researcher wants to look, but he has or she has already uploaded it there. So we dump the whole SQL database into a non-relational database. We don't need the relationships in there. It would be used as a middleware where the normalization would take place. Once this is normalized, well, we create a Neo4j knowledge base and we put it in the query system. So apart from the solutions that I told you before, we have tried to solve the problem of the complex query with this. Some acknowledgements. This is my last slide. Okay, 23 minutes. That's good. My colleagues from the MCCF, Sarah, Mike, Dax, and Juan Garcia Vallejo as the head of the core facility. People from the ISAC, which I have been collaborating. Oran, Mari, Jeff Spillen, and Jonathan Iris, the original developers of Flow Repository. Of course, the ACDC team. I mean, what you would like to keep in touch and to know more about or to collaborate. We are looking also for collaborations into this type of flows. Well, please feel free to contact us or myself personally as a product owner of this.